Okay, yeah, so thanks a lot for the organizers for the invitation to be here. And I'm going to talk about actually two topics. So second topic will be quantum twisted microscope, but before that, I wanted to talk also about some thermoelectric measurements in twisted bilayer graphene. And basically, the story of twisted bilayer graphene is that the following, that if you sort of look at the broader phenomenology of twisted bilayer graphene that has been observed experimentally over the last couple of years, one can basically bin the observables into two different brackets. So first of all, of course, we observe eternal electron physics. So for example, we observe topological phases like Chern insulators and anomalous quantum Hall effect. We observe superconductivity, and also we observe metallic phases in the system. At the other time, we also, of course, observe localized electron physics. So for example, we observe correlated insulators, which basically originate from mod-like insulators that form on the Moray lattice and form these mod-like insulators. And so basically one of the sort of combining efforts to combine those experimental observables into experimental framework was developed by the groups of Andrei Bernovic, Shida Song, but many others. For example, Shidai, Tim Wehling, and Rosa Valenti groups who are working on this, where they were able to map out the Bistritzer-McDonald model onto basically a topological heavy fermion model, where the general idea is that if you look at sort of the Bistritzer-McDonald model and you have these flat bands appearing, you can actually see that the band is not entirely flat over the entire Brilliant zone, but you have sort of very flat regions here close to the sort of Brilliant zone edges where the electrons really are well localized, but you also have these dispersive band regions where the electrons can actually be rather mobile. And so without going into much detail of this theory, because probably there will be more talks about this in this conference. So, but the general idea is that sort of at low temperatures, the heavy fermions can order and basically localize at the lattice sites, but still you get some sort of net free carriers that can sort of be itinerant in the lattice. And so one of the predictions here, so basically this model also allows to do DMFT calculations, which give you sort of the band dispersions at the integer fillings, but it also, B gives you the energy of the quasi-particles and the lifetime of the quasi-particles. So basically for the different ground states that one can compute here, you get basically robust predictions that for the filling factor 0 state, you basically get symmetric bands for electron and hole excitations, as you can see here. So basically the top and bottom Hubbard band, they're basically more or less symmetric. And basically, when you sort of dope the system, you first excite the sort of dispersive regions of the bands. And the other sort of robust prediction is that if you go to the integer filling states, like filling factor 1, filling factor 2, you basically get an asymmetric electron hole spectrum, as you can see here. So for example, filling factor 1 or filling factor 2 states, you sort of, on the electron side, you first sort of dope into the dispersive bands, but on the hole side, you actually first start hitting the heavy fermion bands. And so we basically wanted to test some of these predictions, basically really the symmetry between electron and hole excitations. And in normal transport measurements, basically we are insensitive to this. So in normal transport measurements, we cannot really see a big difference between a sort of electron or hole transport. The only thing that we basically saw in transport measurements is that we saw Shubnikov-de-Haas oscillations when we were on the electron side, but we didn't see Shubnikov-de-Haas oscillations originating from the hole side. So to do this, we basically devised some thermoelectric measurements. In particular, we wanted to measure the Seebeck effect in these TVG devices, where basically the Seebeck effect is sensitive to the majority carriers. It's sensitive to electron hole asymmetries, And this is basically a good measurement technique to sense these particle Hall asymmetry in these devices. Okay, so and this is our measurement scheme. So basically, in two-dimensional materials, it's many sort of standard thermoelectric techniques don't work because we don't have very good thermometers that are smaller than the sample size in the system. So thermometry is not so easy, but one can sort of take advantage of some other things that we can do with two-dimensional materials. And one of those things is gating, right? So basically, we can for example, here make a device which has a split gate on the top here, which allows us to control the carrier concentration in the different device regions separately, and it allows us to set the Fermi energy in the different device regions independent from one another. And basically, it allows us to induce sort of an imbalance of the Seebeck coefficient, when we can induce sort of a step function for the Seebeck coefficient across the device. And the second ingredient, of course, that we need here is some temperature gradient. And the temperature gradient we achieve here with a laser beam that is very sort of low power, but if you shine the laser beam directly at the junction, you create a temperature gradient, which roughly you can approximate to be linear around the junction. And so this type of device then, if we sort of treat the laser beam just as a heating source that sort of induces the temperature gradient, we can basically just measure the photo voltage across the device and extract the Seebeck coefficient from the system. Okay, so basically this is our device. So here is basically our x-axis as a function of filling. So we see gap states appearing at filling factor 2 here and -2. And generally, this is some typical twisted bilayer graphene device that we can have. And basically now what we can do is plot out this resistance as a function of left region of the device, as a function of the right region of the device, which corresponds here to the different axes. So we can basically create this imbalance between electron and holes. And those checkerboard pattern that you can see here is really just tracing all those correlated insulator states with the two different regions. So basically, each of those lines corresponds to one of those peaks, and we can, from the perpendicularity of those lines, we can see that those gating structures are really doing its job and tuning the two different regions separately. So now we can turn on the heating source, and we can shine laser light on it, and we can read out the photo voltage from the device, and you can see sort of that the photo voltage that we read out inherits some of those checkerboard structure, and you can really trace sort of for each checkerboard, you can trace sort of the photo voltage response, and it really oscillates with the same periodicity as this checkerboard. So in order to convince ourselves that this is really the photothermal electric effect that we read out, we can sort of focus on the charge neutrality point here, where we observe this very characteristic six-fold degenerate structure, where of course we get a sign change between PN and NP regions, as expected from many photo voltage effects. For example, photovoltaic effect will give us the same, but what is really the hallmark of the Seebeck effect, of the photothermal electric effect here, is that also in the same polarity regions, so in PP prime, P prime P, and also on the N side, we also see a sign change within this quadrant, and this sign change is really only achievable through the photothermoelectric effect. And similar studies have been previously done here by the Herrero group, Pablo Herrero group, in the past to show that the six-fold pattern really is the hallmark of the Seebeck effect in single-layer graphene as well. So now what we can do to analyze the signal also at integer fillings, we can just take these maps here, and we can take line cuts where we tune one of the regions of the device to a 0 Seebeck coefficient, and we can basically analyze the line cuts here. And so the thing that we see in these type of measurements is the following. So basically, if you look at the charge neutrality point, the charge neutrality point really behaves like what is expected from the Seebeck effect when you tune from electron to hole side. So you can see that really the Seebeck is positive. Seebeck effect is positive on the hole side. It's negative on the electron side, and it undergoes the symmetric sort of S-shaped transition across when we tune across the charge neutrality point. And this is exactly the same behavior as people like Philip Kim here were working out in the past on single layer graphene. So this behavior is really resembling the symmetry between electron and hole excitations, and gives you also the right sign of the Seebeck effect. However, as I mentioned before, also at filling factor 2 and filling factor 1, we actually have gaps. We have electron-hole transitions that we can study in transport, for example. However, you see the signal is very different. So the two things that are different here is A, we do not have sign reversal here, but we actually always keep a negative photovoltage here. And second of all, also across the transition, the sign, the signal is very strongly asymmetric. And so, yeah. Oh, pretty. So there are two ways. It's from the band edge. So the electron 4 filling of the flat bands, right? So we know exactly when the flat bands end, there is a gap. So from this position of the gap, we can know this. And there's a second way we can measure Shubnikov-de Haas oscillations, which then culminate exactly at the band edge. Oh, so it's like below 1/10. Yeah. But also you have several sort of positions to fine tune. You have this one, and then also from the transport. I think from the transport, this is, I mean, we do this, of course, from transport where you have all those peaks that are exactly at integer filling, right? Okay, so basically we see this this sort of different switching behavior or a Seebeck effect at the integer fillings, and we were just trying to understand, sort of course, motivated by the theory, what could be the sort of the ingredients that can give rise to something like that. And we had just assumed, okay, so what happens if we have an electron-hole symmetry in the mass? So if one band is heavy, the other one is light, can we get some sort of behavior like this? And it turns out that we do get an asymmetry between hole and electron Seebeck effect, but we do not get sort of a complete suppression of the one of the sides here. So the necessary ingredient to suppress this whole contribution here is that if we also introduce some lifetime asymmetry, and where we assume that the heavy electrons are very short-lived, meaning that they contribute to the transport coefficient, basically they contribute to the Seebeck effect very weakly, and the signal can be very, very strongly suppressed because of the lifetime symmetry. And coming back now to sort of the spectra that were calculated from the topological heavy fermion model, again, one of the advantages of this model is that it gives us the lifetime of the quasi-particles, right? So basically, the diffusion or dispersion that you can see here in the bands here, this is directly reflecting the lifetime. So you see, so the heavy bands are very, very sort of broadened here. And this ingredient, so basically one can take into the calculations. And if one basically would take these spectra here, and one would basically try to do the MFT calculations, and one can try to reproduce the Seebeck effect originating from the starting points, one would basically get a very similar behavior. So one would get this normal sign reversing symmetric Seebeck effect around the charge neutrality point, and one would get this very suppressed Seebeck effect on the heavy fermion side, on the sort of side of the flat bands, as is seen here in these measurements. Yeah.
All states are states of flat band.
That's right. Yeah. Yeah. Mm-hmm.
The first is the first for the theory, but you're showing data. So, do this just the plot formula, or is it
No. Yeah. So I mean DMFT actually. but Andre knows more details about it, right? Okay, so basically, I think this is just. I mean, I think taking it now in perspective. So I think with many, in principle, these asymmetries, these spectral functions, you can get with many different techniques. I mean, even with mean field, you get these spectral functions. But I think the the big advantage of this model is that one can do the MFT calculation, but get transport coefficients from it, right? So we can calculate actually the Seebeck effect, or we can Tim Roser, Valenti, and Tim Wehling, they're also trying to calculate resistance, for example, which one can later on compare with experiments. Okay, so then I'm trying to shift gears a little bit and talk about a much more technical sort of development that we were working recently in our group. So this is the quantum twisting microscope, and basically sort of the motivation to do this work is from the fact that actually there are by now many of those twisted materials, right? So I mean, I think we have 3 big classes of twisted materials right now. Again, so twisted biographene was the first, but there are many multi-layer twisted systems. There are now twisted TMDs, or hetero homo bilayers, depending on how you stack them, which also sort of involve the twisted degree of freedom. So for example, twisted MOT2, the fractional Chern insulator material, is one of those. There's also big work on rhombohedral graphene, which is aligned to HBN or not aligned to HBN. But bottom line is, so it becomes like a big phase space and a big sort of phase space of combinations that you can sort of combine these materials and try to, via Moray engineering, introduce topological flat bands in the system. Of course, it's people also in our group have made sort of use of the traditional techniques to make those devices. Usually this is sort of a technique that sort of collimates top and bottom layer materials onto one another and basically fixes a twist angle in one particular device. So in principle, you have to make many devices with different twist angles to discover the phase space. And while fabrication protocols have basically improved over the years, still, for example, twist angle disorder and strain variations in this fabrication technique is still something which we are we have to improve. When this technique came along, the quantum twisted microscope, which was basically introduced first by Shahal Ilani actually 2 years ago now, I found this really like interesting way forward, because this technique would allow us to study the larger phase space of these materials and obtain like phase diagrams which are basically twist angle dependent at the same time. And basically the idea of this technique is the following. So instead of like just collimating 2 devices, 2 sheets of 2D materials at the same time, the idea is to separate them, to put one of the layers on this tip, the other layer on a substrate, and make the substrate rotatable. And what you can do is basically you can just combine those materials in different locations. You can change the twist angle. You can also find with this tip first like an unstrained region of the device. You can repeat these measurements many times. And so when we sort of saw this technique by Shahal, we were quite excited. And as I will show you in a second, also what this material really shows is that you can actually get the k-space resolution of the spectral functions here, because you can actually, by rotating the devices with respect to one another, you can basically introduce some k-space vector between the Fermi surfaces, and you can basically this way change the k-space separation between them. And it basically allows us to do some spectroscopy similar to ARPAS. However, unlike ARPAS, with a bit better resolution, because it's a pure electronic measurement, so it's not a photo-excited measurement that we can introduce here. Okay, so basically this is work that I'm going to present. This is done by my group by Martin, who's like assistant professor in Eindhoven now, and Ipsita, who's a postdoc in Princeton, and also in support of theory support of Andrei Bernovik's group, in particular Jonah, helped us really a lot to sort of understand the measurements that we were doing. Okay, so basically the twisted microscope, we followed Shahal's lead, so we first built like a room temperature setup of it, where it's basically just an altered AFM system. We sort of make these special tips here, as you can see, where we grow these pyramids and we sort of colliminate them with graphene. We can take AFM measurements of the tips to identify the plateau structure, and usually we form like flat regions of around 200 nanometers, which are just very well covered with graphene. The measurement scheme that we take is just tunneling spectroscopy. So basically, the pyramid, the tip here has this geometry. So we have this pyramid, we have some cushion layer made out of graphite HBN, and we have the tip covered with graphene. And the substrate is just basically HBN covered graphene as well. And so what we can do here is just we can apply a bias voltage across the tip into the sample, and we can basically measure a tunneling current. And of course, we can also then rotate the substrate, and we can basically continuously sort of map out the tunneling current while we're rotating the device. And so the tunneling sort of configuration you can just see here. So basically, we're sort of applying a bias between sample and tip. This bias, if you do electrostatic simulation, it basically to almost equal parts goes into the doping of the sample area, it goes into the doping of the tip area, and then there's also some electrostatics drop across the HBN substrate here. And of course, if we rotate now, so if we look at sort of graphene, it's just simple Fermi surfaces. If we rotate the sample, we're basically separating the distance in k-space between the two Fermi surfaces, and therefore this separation basically results, so the twist angle separation results in a separation in momentum space, and for small angles this is basically just equivalent to one another. And so basically now we can basically take spectroscopy data, and this is the data that we're obtaining with such a technique, right? So basically here we measure IV, the IDV, and second derivative of the IV. And basically, the voltage, the bias voltage, you can think of translating into an energy axis, and the twist angle here, you can think of translating into the momentum. So basically, we are taking an energy spectrum as a function of momentum here, similar to ARPAS. And if you sort of are familiar with the band structure of graphene, you can already try to guess that there is some spectral information here that resembles a Dirac cone. And basically, one can start to sort of analyzing the spectra now in a little bit more detail. And so basically, this has been done by Shahal already in his first paper. One can basically try to, the two features that one sees here in the second derivative quite clearly, so it's a little faint here, but basically you can see two types of lines, right? So you see this X-shaped line, which you see here as well, and you see this hourglass-shaped line, and those two lines are basically explained in the following way. So those are basically corresponding to different scenarios where energy and momentum resolved tunneling transitions are allowed. So again, to tunnel from one layer to another, you need to match energy and momentum. And so this X-shaped feature here is the onset condition where the Fermi energy and the top and bottom layer, they coincide. And you basically, for a specific twist angle, you just also find the momentum matching between the transitions, and then tunneling is possible. And this is really the sort of linear transition that we can see here, and it's mostly related just to the voltage bias that we can apply here. Yep. Yeah. Right. Yeah.
So I presume that the left one is theoretical.
Yeah. Yeah.
And so the question then is, what is controlling the V shape?
Right. So. Right. So actually, this is the data from Shahal's first paper. Yeah, and this is our data. So. No. This is our data. Yeah. Oh yeah. Sorry. What? Yeah, so okay, so I just wanted, so why make this comparison? So because this will become important in a second. So they use a WSE2 tunneling barrier. We use a HBN tunnel barrier. So the HBN tunnel barrier allows us to, it has a much higher dielectric breakdown voltage. So we can actually tune to much higher voltages. Okay, so this is why you see here, so basically here at 0.7, already conduction basically takes over because the WSE2 becomes conducting. Right, so you just bias it across above the gap. And HBN, you can actually, I mean, in the paper we shown we can even tune it up to 3 volts, so more than 3 times higher before we reach the electric breakdown. This is related to just the area of the interface. So this is in every device. This is not like. Okay, so so in the other conditions, so again, linear condition, this is the onset, and then there is a nesting condition, and this will become important in the last 5 minutes of the talk. So nesting condition is just the fact when the two top and bottom layer band structures, they run in parallel to one another, where really you get an extended K-space region where tunneling is allowed, where basically the bands just run in parallel and you have like a lot of tunneling transitions. So I probably still have 5 minutes. Was that? No, it was not. Okay, all right, okay. Okay, so, and basically with those nesting and onset conditions, we can understand these features that we observe. And I have to say, of course, this is not just limited to single layer graphene, because we took, for example, many different measurements on single layer to multi-layer graphene tunneling and so on. And this is, for example, tunneling into bilayer graphene, tunneling into tri-layer, tetralayer, pentalayer. All of those sort of conditions that you see here are some sort of nesting or onset conditions that basically are sensitive to the band structure in which you tunnel to. And if you basically use a single simple tip structure from which you tunnel from, you can basically, from all these measurements, you can reconstruct the band structure of the material, and you can define band structure parameters and so on. And of course, for multi-layer graphene, this is more or less known. You can do this for ABC, for rhombohedral graphene, where I think maybe band structure constants are not entirely clear, especially as a function of displacement field. So we're doing this right now in the lab. And so this is basically shows a little bit the spectroscopic sort of power of this technique. So the other thing which we also can do in this technique, we can apply pressure. So because we have like such a narrow tip region, we can press into the device, and we can basically apply pressures up to some gigapascals. So this sort of measurement here on the right, this 3,000 nanonewtons that we apply force on the device, this corresponds to something like a 1 gigapascal in pressures that we can apply. So so one can, with this, one can of course change also the band structure of the material. So now I can just showcase here in the AB bilayer measurements. So in AB bilayer graphene, there are 4 bands. 2 higher energy bands are separated exactly by gamma 1. This is the interlayer tunneling parameter from top and bottom layer. And this gamma 1 parameter really just sets the separation between the top and bottom bands. So, but of course, because it's the interlayer tunneling parameter, if we squeeze the layers between the two materials, we actually enhance this tunneling parameter, or the hopping parameter, and we can basically sort of push these bands to higher energies. And this is something which you can see here. So these lines here, they correspond to the nesting conditions of the these higher energy bands, and you can see. So if we press, these sort of bands are pushed out in energy. So really, with just by with this technique, we can sort of pressure control the band structure of the material. And I think for this will be particularly interesting later on if we can do sort of tunneling into the superconducting phase. So it would be very interesting to see how the superconducting phase changes under the pressure. Last but not least, about characterization. So those are also some maps that show the high reproducibility of the results. So in principle, really, we can take any different tips, any different samples, we can rotate them, we can sort of scan to different positions and so on. And really, so those are sort of quadrants which show different sort of combination of measurements that we have taken, and all those features are highly reproducible. Okay, so the last 5 minutes, I just want to show some sort of unexpected results that we have sort of observed while we were sort of getting warm and with this technique, is one thing that we observed at sort of relatively high bias, so at around 1 volt on bias that we applied to the device, we observed actually that the nesting condition, as you can see, it started splitting. So there are basically 2 nesting conditions that it forms to, and you can also see it here quite nicely, where sort of the main nesting condition faints away, and then there's a second one branching out of this. And as I maybe explained in this slide, in principle, the nesting condition lives on the fact that the band structure of single-layer graphene is just linear, and that the linearity is kind of persisting quite far into the K-space. So in principle, in a scenario like this, for just a perfect Dirac cone, we should not see any second nesting condition, because the bands always have to run in parallel to one another. So first we scratched our head, so what is this feature here that produces this nesting? But it was clear that this nesting is produced by some small nonlinearity. And basically, to highlight that really just only a small nonlinearity can give us such features, so this is just a cartoon picture of sort of, if we assume that the bands are not entirely parallel, if we assume some small nonlinearity, then basically instead of like 1 extended nesting condition, we actually get kissing points. We get 2 kissing points where sort of the bands run in parallel, but of course they don't run in parallel over the entire K-space. So okay, so basically we assumed that really only some small nonlinearity can give it to us, and then of course we scratched our head a little bit and started doing modeling to understand what type of nonlinearity could it be, because in the end of the day we measure something at room temperature, so we of course assumed first many different trivial explanations which are seen here, and basically let me just walk you through these. So for just a single for a nearest neighbor tight binding band structure that we can take here, of course, if you sort of go to really high energies, at one point the band structure of course starts to become nonlinear. So that's of course assumed here. So for example, the first nonlinearity that you see here is in the M points, when you are at around 2 electron volts per 2 electron volts in the energy. However, this sort of 2 electron volts, if we look sort of at the calculated tunneling spectra, this would correspond to electrostatically to sub-bias voltage of around 7 volts, which is basically 5 times higher than sort of the nonlinearity that we observe in our measurements. So bottom line, so basically we, because it's 5 times higher, we thought we can exclude this. The other sort of scenarios was of course strain. So we were wondering if strain could produce such a feature as well. But one thing which speaks against strain is that we can test our device in many different regions of the map, and we can change different tips and devices, and basically all of the energies at which we observed the nonlinearity were the same. And really these strained sort of maps, they don't produce a nonlinearity, but they produce actually more like a gap-like spectra due to sort of the misalignment of the Fermi surfaces. Third, next nearest neighbor hopping, this was also famously reported to produce some nonlinearity, but these next nearest neighbor hopping terms, they give actually some electron hole asymmetric deviations, and also at much higher voltages than what we observe in our devices. So basically, our sort of best sort of explanation that we can achieve is from electron renormalizations, and I think this was first introduced by Paco, right? So who is here in the audience, and the idea here is that if you tune the Fermi energy in graphene very close to the charge neutrality point, then the electron-electron separation, or the density of the electrons, becomes so weak that the electrons stop feeling one another. So they basically stop screening one another, and therefore the Fermi velocity at the charge neutrality point can be somewhat enhanced. And if you basically start filling the electrons back into the system, at one point screening takes over again, and then the electrons screen each other quite well, and then the Fermi velocity just reduces. Okay, so in this type of correction can be very small. So usually the correction is from a Fermi velocity of 0.85 to a Fermi velocity of 1.05, and you can see here, so really this can be just an effect of 10 to 20% that arises here, and sort of this is the formula which describes it all. This is basically a logarithmic correction onto the sort of linear direct dispersion. And so if one looks back in literature, so actually this has been observed in many places around 2011. So the first paper was by Andrew Geim, where they did Shubnikov-de Haas oscillations at low temperatures. They observed this enhancement. Then here Lanzara from Berkeley, they also observed in ARPAS measurements this correction, and also Joe Stroschel, Philip Kim, they saw it in STM measurements. So basically, if we include this type of correction now into sort of our model, then we reproduce the same type of low energy correction here, which produces a splitting. The splitting is also exactly like the one which we observe here. So we have a smaller branch which ends, and a higher branch which sort of takes it over, and more, yeah. 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 It appears at larger K, yeah. Yeah, so basically, right, I mean, so you have to think in the way of, I mean, basically you have to think on how the bands overlap. So basically this is sort of the cartoon picture for linear dispersion, but then this is the sort of cartoon picture for what happens for this type of linear correction. So you will see that basically these kissing points that you're getting, right, so the two kissing points that you're getting for the slight nonlinearity, they actually, for low sort of, for low bias, they run very closely with one another, and only at high voltages you can see the splitting. But it's basically, it's still sort of, it's still the nonlinearity is at charge neutrality point, but the way it's sort of, the bands sort of merge together. This is what gives the nonlinearity. Okay, so you can actually, so in the paper we also plotted how the nesting condition just evolves over the entire sort of energy range, and you can see that it's at low voltages it just goes together, just crosses, but it stays together, and then only later you can see the separation. Okay, so and basically. Okay, so basically, last but not least, so what we were able to show is also that not only the nesting conditions, but actually also the onset conditions that we obtain can give resolve this effect. So that it's also becoming slightly nonlinear. So there's a second observable that pinpoints to this nonlinearity. And then the good thing about the QTM, which I found while doing this measurement, so we can actually repeat this measurement just 10 times on the same device, in different locations, for different tips and for different samples. We can just sort of bin these measurements from 10 data sets, we can bin them together, and we can basically then fit it. And so basically the fitting parameters that we found from this binning of the data is that really Fermi velocity is 0.85, and alpha, which is the basically resembling the strength of the electron-electron interactions, is around 0.3, and this is very well comparable, actually, to mostly comparable to the STM data, which was also done in a very similar devices. So this was also HBN encapsulated devices, so it's a very similar dielectric environment in which they did the measurements. It's also a tunneling spectroscopy measurement. So we found very similar numbers to what they have found before. Okay, yeah. A lambda is very large, right? So this is the cutoff frequency. This is order of bandwidth of graphene, right? So this is in the order of 6 eV, right? So this corresponds to I mean, lambda is basically fixed, right? So lambda is, right.
Right, on that, so lambda is the open.
Right. So lambda is the cutoff frequency, so it's like, usually it's like defined by the bandwidth of the entire pi band of graphene, which is sec CV, of course. No, it's the entire bandwidth. Yeah, yeah, yeah. Yeah, exactly. You have the inventor of this sitting next to you, right? Yeah, yeah, right, yeah. And the other thing is, I mean, this lambda is also the reason why we see this effect also at room temperature, is because this effect is not very sensitive with temperature because lambda is so big. You basically supposed to see this effect probably at 1,000 Kelvin as well, right? Okay, so and basically, so I think so basically, okay, I have to say, so we used the QTM to study some physics which was already known, but I think it's for me it was quite interesting to see how sensitive this QTM technique is. It can resolve like small, tiny deviations of the Fermi velocity in band structure, even at room temperature, and it's kind of, I think, a very sensitive technique to study small corrections to the band dispersion. And so the next thing is we have now a low temperature setup which is working. So we have a 12 millikelvin dilution refrigerator, 911 Tesla magnet. We use piezoresistive tips with which we can also scan and find the sample. So this is just a scan with such a piezoresistive tip over the device. So we don't need optics in the dilution refrigerator. We can just like tap and find our sample and then also know exactly at which position we are taking the measurements. And so I think, just to give a little bit of an outlook, so what I would be excited to see or to do as a community, because now there are several groups who are trying to build these QTMs, is really, so one example is just to probe the band structure of rhombohedral graphene under displacement field. So I think one of the things in the sort of exciting time that we have in rhombohedral graphene, you always are limited by these device architectures. You have top and bottom gates, so you cannot do easily STM on it, you cannot do easily ARPAS on it, right? So in order to get some spectral information, maybe this is a technique that could give some information about it. Then I think I just talked to Leonard Glasman just last week in Aspen. So they're posting a paper where they just calculated all the different scenarios of how a superconducting order parameter would appear in the QTM measurement. So it seems to be that QTM measurement, because we rotate the sample and we do tunneling into that, it would be very sensitive into tunneling into a superconductor, and would be very sensitive because of the rotation to the order parameter of the superconductor that we're probing. So I think there is hopes that really some of those superconductors that people observed in the field, maybe one can really directly image the superconducting order parameter in them. And again, at millikelvin temperatures, most of those materials are superconducting. And then, for example, probing the spectral function of fractional Chern insulators, I'm pretty sure this is also, there are also some theory papers around it. So, and with this, so thanks a lot for your attention.
Questions?
So then, regarding the FTI,
Yeah.
usually FTI is seen when the sample is substrate.
Right.
Okay. Would you
So exactly. So this is the thing. So in a transport device or in a capacitance probe device, like what the people are doing, it would be capped and that's it, right? But here, we're actually doing this experiment as I speak now, right? I mean, we can introduce the gates to the tip, we can introduce the gates to the substrate, and we can just have a displacement field measurement across the tunneling interface. Right. So I mean, all you need to do is you need to have a separate electrodes containing this graphene layer and the graphite, and then you have a displacement field that you can apply. Yeah. So and actually, and this is we already have tips like this. You just need to construct new electrodes, separate the layers, and then it works. Yeah. It's actually, I mean, actually, whatever people came up with in van der Waals materials, whatever device architectures or measurement schemes, you can, in principle, totally implement it in this architecture. Oh.
I have a question about the first half.
I have a question about the first half of about the thermoelectric measurement. Under some assumptions, there is a relation between the thermoelectric coefficient and entropy. Was there any attempt to measure entropy change?
So, exactly. So, this is something which we couldn't do with this architecture. So, and the reason is that with this laser beam, we don't have exactly, don't know exactly the temperature at which we're exciting. We kind of have assumptions, we have calculations, we can assume heat capacity and laser power and so on, but we don't exactly. But right now we sort of went the next step, so we designed fully on-chip heaters. I mean, similar to actually what Weizmann group is doing for the thermal transport on the quantum Hall sense. So it's a similar technique, where we have on-chip heaters, we have on-chip thermometers, and where we can basically, then one can do that. Then one can sort of measure all those parameters and extract entropy per particle, right? So this would be, yeah. So this is work in progress now, yeah. But nobody has, I'm not aware that anybody has done it yet. Yeah.
So a question for the second part of the talk. When you bias the tip to these large values, is it important to consider quantum dot physics, meaning that you would locally vary the chemical potential under the tip, but outside of the tip region, you would have the global gate potential, or is the tip just too large that it is not?
Oh, it's too large, yeah. I mean, so actually, so it's tip is, I think, between 200 nanometers and a micron. So this is too large to, okay. I mean, also, the tip is not isolated. The tip, right, I mean, we send a current through the tip, so it's not like there's no confining potential on the tip. So it's just a conductor, yeah, so it's not a quantum dot. But actually, Shahal and Ani's group, for example, they used a very cool technique. So they found defects in the substrate, which is like point defects, which is like angstrom scale, and they were able to use it as a quantum dot to sensing, right?
Yeah, so I have a very quick question. Depending how you answer, I have a quick follow-up. So on the dispersion, I'll then ask the two together. So in the dispersion that you showed up, which changes from linear to the logarithmic correction piece, can you put it there for a second, the slide?
Okay.
Yeah. When you make your measurements and you worry about nesting and so on, you're presumably doing it at some temperature, which I haven't seen what the temperature was. Is there any temperature dependence on the thing? So that, and then if so, are there any additional corrections perhaps due to other things?
Yeah. So
phonons, for example.
So exactly. So this measurement was done at room temperature, just because we didn't have the low temperature setup yet. So it's the first thing you do experimentally. You just and so what our theory collaborators did, however, is they sort of tried to introduce a temperature dependent effect. Right, and so the temperature-dependent effect, as far as I understand, can enter two ways. I mean, first of all, you introduce some temperature KBT on your Fermi surface. That's the one thing, right? And then the other thing is, I guess one has to look at whether some of these alpha or lambda, they are temperature-dependent.
Right,
and so,
but this is Coulomb, right? So
yeah, exactly.
So phonons, for example, that's what I was. In addition to that, because it's probably a zero temperature calculation.
Right. Yeah. So phonons, yeah. So phonons. Also I have to refer to Shahal. So Shahal at low temperature saw some phonon resonances connecting the Fermi surfaces. So they were able to see like a phonon in that. So at room temperatures, of course, we have a lot of phonons. Of course, at room temperature, at low temperatures, they only see them because they're like very sharp. But at high temperatures, of course, we have tons of phonons. So what the phonons do is they just broaden things, right? This is my assumption, yeah. Right, right. So, right. So basically, maybe this is the way to see it. So you see, so there's like a small correction, which is sort of enlarging the Fermi velocity here, and then it's sort of making it smaller again. So this is sort of this is the correction here that we see. So if you start like overlaying those two band structures to one another and trying to see where they sort of become parallel with one another, you will find that there are like two nesting conditions which are separate. And this is something which, again, one can best explain by looking at sort of these type of scenarios here. Okay, so if you look at sort of this type of concave correction that we see, you will find that there are really two nesting conditions. So here, for example, this at sort of the large tail, but also here, because you're close to charge neutrality, you see here also there's like a larger sort of parallel line. So all of those two combined basically give you this nesting at this voltage, and this voltage just corresponds to the curvature of this, right? So basically, I think there's no other way than just to calculate it, right? And so what in this calculation, so here, for example, in this calculation, one just basically assumes these parameters, alpha and Fermi velocity and lambda and whatever, right? And this is where this sort of curvature gives you the right nesting. So yeah. And then you can compare those numbers, those parameters that we extract, you can compare them to literature values, right? And then what convinced me is that really we get the right literature values. We get 0.85 on the Fermi velocity and alpha of around 0.3, which is consistent to what people have reported before, right? Right. Right. It's in the order of the bandwidth of single-layer graphene. Yeah. So yeah, exactly. So, but this is literature value, this lambda, right? This is right, right, yeah. Right. Yeah. So okay, so right. So okay, so the difference between those three measurements. This is suspended. This is suspended. This is on STO. This is ferroelectric. So this is, and this is on HBN. So those are three different parameters. So those are three different sort of dielectric environments, right? Okay, and so and then there's more literature. Like maybe you can find 15 experimental papers or so. So I would say also that here the effect is a little bit overestimated. So I think if I compare sort of to the other following up work, so later work, the effect was usually 10 to 20%. Here you see that it's almost like 300%, right? You know, so I mean, I would say that this is sort of maybe if you suspend a device, also strain matters, and right. So right. Yeah, both sides. Right. Yeah, so it's both sides. So HBN here, the green one, and here, right? Yeah.
Okay. Thanks very much again.